Well, good morning. Today I'm going to do a video, essentially so we can cover the last section 3.7, and it deals with how do you solve inequalities, and in particular polynomial inequalities and rational inequalities. And we're going to start by looking at how do you solve the polynomial inequality. What do they look like? How do you solve them? And how do you express the answer? Because we're typically going to be solving these inequalities, and we're going to be using interval notation. All that means is that when we're finished, our answer will look something like the solution is all values of x between -infinity and 4, union from 4 to infinity, things like that. And they'll typically be a lot longer than that, but that's essentially what we mean when we say express your answer using interval notation. Now, if you think back to a different world, we know how to solve linear inequalities. And when you add 4 to both sides, and then you divide both sides by 2, you get that. And you would write the solution down in interval notation like this. A square bracket at 6 means you can use 6. And since x has to be greater than 6, you say 6 to infinity. And so that would be the solution to this linear inequality in interval notation. So what's the difference with polynomial inequalities? Well, essentially, this technique doesn't really work. And we have to create and look at a different technique. So first, let me show you what some examples of a polynomial inequality might look like. The simplest ones look like that. This is a polynomial, but it's all been factored for you. And you're typically going to solve when, for what values of x, is this thing going to be greater than or equal to 0? And that's your goal. So for what values of x would be, another one might be something like x plus 3, x minus 2 cubed, 2x plus 7, let's say less than 0. So you'll have an expression, a polynomial expression. If you FOIL that all out, it would be a polynomial. And it has to be the values of x, which makes this polynomial less than 0. And we will give that answer using interval notation. Anything that's factored greater than 0 or less than 0 is our friend, because we're basically, they've taken away one big chunk of the problem, and that would be you need to have these things factored greater than or equal to 0 or factored less than or equal to 0. So if you don't get one factored, that's going to be another job for you. So for instance, you could get that is an example of a polynomial inequality, but the problem with this one is that it's not factored, and you need it to be in this format to be able to solve it. So you would have to do another piece of work, which is essentially factor the left-hand side. Now, if you got something that looked like that guy, that also counts as a polynomial inequality. In this case, the polynomial is an x squared. That's even worse case scenario. In fact, in a way, that's the worst you could get, because what you would need to do is first, always make it greater than 0 or less than 0, right? That's the format. Also, kind of always factor it as much as you possibly can. And so that might have been the original inequality, but this is the inequality, the form it needs to be in for us to solve it. So here are some examples of polynomial inequalities and what you would need to do in some cases to do it. For instance, if I looked at this one here, and I just realized I put a 4 there when I meant to put a square. if I did this one here, I would pull out x squared as a common factor, and that would get me this. But I can do a little bit better, because x squared minus 9 can be factored as an x plus 3, x minus 3 greater than 0. So this is the guy that we'd actually use to find the solution. Not the original, although the question might do it that way, it might give you it in this format. That's not where we end up. We need to factor it as much as possible. And then once it looks like this, then we can solve it. So let me take you through the list of things that you need to do to solve a polynomial equation. So I'm going to take the worst case scenario. Let's take this one here. So suppose you were being asked to solve that. The first step, step one, is to make sure that this gets factored and that it ends up looking like a whole load of things factored, greater than 0 or less than 0, whatever is appropriate to the question. So I'm going to pull out x squared as a common factor. And then going to factor that because it's a difference of 2 squares. And we get to there. So step one would be to take the original and to rewrite it in its factored format. Now, the good news is that most questions, you already have that. That's good, because then you don't need step one. Step two is we find what are called critical numbers for x. Critical numbers, critical values, critical numbers for x. Now, these critical numbers for x are essentially the values of x that make any of these factors 0. So I'm just going to write this guy down again. Here is our inequality. And the critical numbers are at x equals 0, the thing is equal to 0, at x equals -3, and finally at x equals 3. So there are 3 critical numbers, and they are going to help essentially separate out the places where this will work and the places where it won't work. Now, once you've got your critical numbers, you then move on to step 3. And step 3 is create a number line. And use test points to find the solutions. What do I mean by this? Create a number line and then use test points. Well, I know that all the critical numbers are 0, -3, and 3. So a reasonable number line is a number line that has all those numbers in it and a little bit extra. So I'm going to say -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, and so on. Now, this number line actually goes on forever, but the only values we need to see are based on these critical numbers. Now, on this line, the first thing I'm going to do is put x equals 0, and I'm going to put a little open circle there. At x equals -3, I'm going to put a little open circle. And at x equals 3, I'm going to do a little open circle. And there are 2 choices here. You either make it a solid dot, like that, or you make it an open circle, like that. that actually gives you information. If I put a solid dot on these three values of x, that would mean I could use that value of x in my solution. If I use an open circle, it means these are critical numbers, but I cannot use that value. So you might say, well, how do you know if you can or can't? It's pretty simple. Do you see this? This inequality says that all of this has to be greater than 0. If I plug equals 3 in here, I get an equals 0. So since that is a greater than, everybody here is going to be a circle, right? That's essentially it, right? So if that had said greater than or equal to 3, greater than or equal to 0, then these would become solid dots and I could use them in my solution. So that's what the number line looks like. Draw a number line with numbers that can at least contain these and maybe a couple extra. On the number line, put the critical numbers, their position, and either a circle, right, an open circle, or a solid dot, depending on if that says greater than, everybody is an open circle. If that says greater than or equal to, everybody is a solid dot. Now the test points, which is this bit. Essentially, what we've done here is taken the number line and kind of broken it a little bit. Try to find some green pen. All my green pens are gone. Okay, so I'll use red. And what we've essentially done is broken the number line into 4 regions, right? 1, 2, 3, 4, right? I guess I'll call them letters of the alphabet. There's region A, here is region B, here is region C, and finally here is region D. We pick a test point. Any number will do as long as it's in that region, but you should really pick nice numbers to work with, right? Don't pick 3.22 or something. It's just not necessary and it makes your life hard. So I'm going to do a test point for A, for B, for region C, and in this case, one more region D. So who would I choose? Well, in region A, I could choose -4. I could choose -5. Technically, I could pick -1,000,000. I wouldn't want to, but I could. Anything in this side would do. And I'm going to pick x as -4. Now, in region B, I could pick -1 or -2. And you probably already guessed I'd probably pick that one. In region C, wouldn't I pick either a 1 or a 2? I like making life easy, so I'll pick a 1. And over here, I'm going to pick 4. So here are my 4 test points. So what we have is x squared, x add 3, x minus 3, right? That's the expression that's here. For each one of these test points, I'm going to plug it into this question, and I'm going to get a numerical answer. Now, here's a little thing that's kind of interesting, and it actually speeds up the work. I don't care what the number is. I don't care if it's +40 or +17 or +1,000,000. I'm only concerned, is the answer positive or negative? And because of that, you can actually do these calculations relatively easy, even without a calculator. So for instance, my first test point, right, was x equals -4. So let's see what we get. We get -4 squared, -4 add 3, and -4 take away 3. Now I could actually calculate that out and pretend I know the answer, and it ends up being -512. I don't care about 512, only that it's negative. So, and I don't want to have to do big calculations, so I do this. If you take the number -4 and you square it, the answer is positive. If you take -4 and add 3, you get -1. If you take -4 and you take away 3, you get -7. And if you multiply a positive thing with a negative thing with another negative thing, the answer that you get is positive. Good. So I'm going to put a little plus there. And in fact, anybody in region A is positive. So I put lots of pluses in. And that's essentially saying everybody here is positive, right? Any value of x you choose, this expression is going to be positive. And you might say, well, how can you do that with one test point? The math says, if these are the only places where something is zero, right? Zero is like a transition point. You can either go from plus to minus, but if you're going to go from plus to minus, don't you have to pass through zero if you're a polynomial? Right. So since there aren't any more zeros to the left here, whatever that is, it has to stay that. It can't go pluses and then later on turn into negatives, because for that to happen, shouldn't there be another zero over here? And we know there aren't any. So essentially, once you choose a test point in a region, if it's plus, everybody's plus. If it's negative, everybody is negative. Now, the next one would be at x equals -1. And if I plug in -1 here, what do I get? I get -1 squared, -1 odd 3, and -1 take away 3. And -1 squared is positive. That guy times that is a positive thing. And these two are a negative thing. So this time the combination is negative. Right? If you multiply a positive by a positive and then finally finish with a negative, that combination makes everybody here negative. So I'm putting a whole load of negatives here. And you go through all the other ones in the same way. This is x equals 1 now. So you go -1 squared, -1 odd 3, and -1, not -1, caught myself, +1 squared, +1 odd 3, and +1 take away 3. That's better. +1 squared is positive. Those two guys get me positive. And this guy here, I believe, gets me negative. And so this combination is also negative. Here we go. So any number in the range between 0 and 3 is going to be negative. And for the last one, x equals 4, we get -4, sorry, there I go again, +4 squared, 4 add 3, 4 take away 3. And that guy is positive, that guy is 7, so he's positive, that guy is 1, so he's positive, and so the final answer is positive. So on this end, I now know that everyone is positive. Okay, so hopefully you're with me. Step 3 is where the main solution process happens, right? You do your number line, you put where the critical numbers are, in this case, -3, 0, and 3. That breaks the region into 4. For each one of these 4 regions, you choose a test point, a value of x, any guy you like, but keep them nice. For each test point, you find the value of this, and sometimes the answer is positive, and sometimes it's negative, and that goes here. Now I'm just going to redraw this line. You wouldn't normally need to this, but since I'm going to be pointing at things, I think it's better if it's just a little bit more here, right? So what we got, we have -5 and all the other numbers that go. And at -3, open circle, at 0, an open circle, and finally at 3, an open circle. And we know that in this region, everybody is positive. In the next two regions, everybody is negative. And in the end region, everybody is positive again. So we now are going to do step 4. And step 4 is find a solution using the number line. Now, I am interested in when is this polynomial positive? The number line tells me for what values of x you get a positive answer, and for what range of values of x you get a negative answer. So when I look at this picture, I say, oh, anything from -3 or less, the answer is positive, and anything from 3 or more, the answer is positive. So our solution in interval notation would be anything less than -3, don't use me. Can't use -3. Why can't I use -3? Because it's an open circle. Open circle means you can't use that value of x. A solid dot means that you can use. Right. So that means you can't use it. This means you can use it. Now, do I have another place where it's positive? Yeah, I have from 3 onwards. Union 3 onwards. And again, you cannot use it. So I hope, I mean, there's a fair amount in this, but at least the process, for the most part, is the same process. Sometimes you don't need step 1. That's maybe the only major change. Now, I want to show you a slight variation on that question. Right. Suppose I changed it to greater than or equal to 0, right? That's the only difference I made. What would happen in this number line is that these 3 guys would now be usable. So it'd still be plus in this range, negative in these 2 ranges, and plus in that range, right? So it would be usable. The solution, if you went through the entire process, but I don't really need to because this number line has it, would be anything less than -3, but now you can use it, union anything from 3 onwards, and you can use it. So do you see the difference that a greater than or equal to makes to the solution compared to just being a greater than, right? So that was greater than, that was greater than or equal to. Little subtle difference, but that's the thing that you tend to make the mistakes on, not putting curved when you should. Curved is when this guy says greater than 0, or if it says less than 0. Square brackets, meaning you can use me, is when this says greater than or equal to 0 or less than or equal to 0. Now, one more situation. Same question, just turn the tide. Just to show you the subtleties in this question, right? Everything that I did here would be identical. Even that would be pretty much identical, right? This would be circles. Why? Because it's less than, right? Open circles. Now, if you're looking for when it's negative, let's see if we can figure that out. Well, this is the wrong answer. Oh, everybody from -3 to 3, it's negative. Well, not quite. At x equals 0 isn't the answer equal to 0, and therefore you can't use it. So that's the wrong solution. The correct solution would be -3 up to 0, but you can't use 0. Starting at 0, and you can't use me, to 3. So do you see the subtle difference is the value of x equals 0 was not usable in this question. Now, If it had been less than or equal to 0, then the solution would have been everybody, oops, curve bracket, everybody, and I can't do that, third time lucky, everybody from -3 to 3, and square brackets on them as well. Okay, so be aware that greater than, or equal to, less than, or less than, or equal to, do make a difference, right? They do change the answer, even if it's only subtly. And of course, in a normal day-to-day homework question, you certainly would maybe write quite as much as I've just done. So let me zoom over to the homework and I'll pick one. The good news, as far as I'm concerned, is that once you know how the process works, really the question just becomes, follow the process and you'll be fine. So can you see this one's already factored and it's a less than 0? This one is already factored, it's a greater than or equal to 0. There's another one greater than 0. This one is the same question. The only difference is they give you a choice and you pick the right one. A little bit different in the sense that you do it. And this horrible one here, you have to do step 1, right? And step 1 is basically make it a factored polynomial greater than 0 in this case. And that's the end of the polynomial ones. So I'm going to pick question 2 and question 5 to just give you 2 more examples of polynomial inequalities. So this is my version of question 2, and let me switch over. Take me a few moments. Here we go. So I want to do question 2. It's nice and factored, which is good. We like that. Okay. So you're going to get kind of the sped up version of this one. Already step 1's done. Step 2 is find the critical numbers. So x equals 1, x equals -2, x equals 4, and finally x equals what? -8. So I'm now going to do a number line. And I know I need to at least have -8 in it. So how about -10, -9, -8, -7, -6, -5. There's -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, right? Nothing wrong in having a few extra. So there's the number line. Now, in this case, it's greater than or equal to 0, which means that these x values are usable, right? They're allowed to be in the solution. So if I do a dot here, a solid dot at x equals 1, 1 at -2, sorry, my mistake, pretend that's not there. There, there's 1, that's good. That's not there. There's -2. Here's 4. And away over here is -8. Okay. We good? There are only 4, right? That, I wish I could rub that out, but I can't. That's not there, right? That one is, 1 is, and 4 is. Now I'm going to do test points. Those little dotted lines I put in are really only for emphasis. You don't need them if you don't want them, but they kind of make my life a little bit easier to see that there are actually, 5 regions this time. So this guy over here, I'm going to pick -10 because I want to. In this region here, I don't know, I'll pick -4. In this region here, I'm going to pick 0 because I want to. Here, I'll pick 2. And lastly, over here, I'm going to pick 5 because I want to. So pick any point you like in each of these 5 regions, and these will give you your test points. Now, for each one of these guys, we then figure out whether the answer is positive or negative. Let's do x equals 5. If you wanted to do this one, it would be 5 take away 1, 5 add 2, 5 take away 4, and 5 add 8. And let's see what that gets me. 5 take away 1 is positive, 5 add 2 is also positive. 5 take away 1 is positive. Oh, everybody is positive, so the answer is positive. So make everybody here positive. Let's do negative 10 then. If I did negative 10, I would get negative 10 take away 1, negative 10 add 2, negative 10 take away 4, and negative 10 add 8. What does that get me? That guy's negative, so's that one, so's that one, so's that one, which makes a positive answer. So everybody over here is positive. Now x equals negative 4. That's this one here. X equals plus 4. Next to 4 is this one. Right. Back to my right hand side. Negative 4 is in this region. What am I going to get? Negative 4 take away 1. Negative 4 add 2. Negative 4 take away 4. Negative 4 add 8. This piece is negative. So's this piece. So's this piece. But this piece is positive. 3 negatives and 1 positive give me a negative answer. So everybody here is negative. Right, x equals 0 now. We get 0 take away 1, 0 add 2, 0 take away 4, and 0 add 8. And that gets me a negative. That's positive. That's negative. And this is positive. That combination ends up being positive. This one here, x equals 2. Let's see what that gets me. 2 take away 1, 2 add 2, 2 take away 4, 2 add 8. In my case, that's positive 1, positive 4, a negative guy, and a positive guy. So that combination gives me negative. Right. Now, we are only interested in when this entire thing is positive, greater than or equal to 0, right? Positive. So it's good in this region, right, from here to here. So that would give me, let's see what that means. Anything less than negative 8, including negative 8, including it because greater than or equal to 0, including it because I put a solid dot there. Union. The next area is from here to here, right? From x is negative 2 to x is 1. And again, you're allowed to use those two critical numbers, x is minus 2 and x is 1. And lastly, 4 and beyond. And that is essentially the solution to this polynomial inequality. Okay, hopefully that's going well. Version of this, let's look at a version of question 5, which is x, 1 take away x squared cubed has to be greater than 3 lots of 1 minus x squared cubed. Okay. Now, we need a step 1 in this. Step 1 is essentially we have to make this a polynomial greater than 0. So what I'm going to do is I'm going to subtract 3 1 minus x squareds from both sides. So I have that guy, take away 3 lots of that guy is now greater than 0. And then I'm kind of lucky because it does contain a common factor. And the common factor is 1 minus x squared cubed times x minus 3 greater than 0. And that looks really nice, except it's not as good as it could be. We need to factor this as much as possible. What you might not notice is that 1 minus x squared can be written as 1 take away x, 1 plus x. It is a difference of 2 squares. That means we now have this guy. Now, if you've got two things multiplied together and the product is cubed, algebra says you can split it into 2 separate guys cubed, and it's the equivalent to it. So there, that is step 1 now finished. Our critical numbers are going to be x equals 1, x equals -1, and x equals 3. So I think over here I'll do my number line. And I need to have at least, what, -1 in it. So how about -3, -2, -1, 0, 1, 2, 3, 4, 5. There's plenty. And it is greater than 0. So these 3 critical numbers cannot be used in the solution. So at x equals 1, I'm going to do an open circle to indicate I can't use it. At x equals -1, an open circle. And finally, at x equals 3, an open circle. And I'm going to put in my little invisible dotted lines. They're really cosmetic, but they help me to find test points. Switch places. Okay, for x equals 1, right? We're going to use this guy here, right? So for test point x equals 1, you get 1. Why am I doing it? Test points. Have to pick someone from here. So my test points are actually going to be x equals -2. That's fair. In this region, I'm going to put x equals 0. In this third region, I'm going to pick x equals 2. And in that last region, I don't know, 5. So these are our test points, right? Our test points come from one of these 4 regions, right? Not from these numbers, but from one of the 4 regions. Now, for x equals -2, you're going to have 1 take away 2 cubed. And then I did that mistake here. It's -2, so 1 take away -2 is 1 plus 2. Then it's going to be 1 take away 2 cubed. And that guy there is going to be -2 take away 3. So 3 cubed is positive, -1 cubed is negative, and -2 take away 3 is also negative, which means that this thing, right, this thing is overall going to be a positive. So everybody is positive. X equals 0 is my next one. So what's that going to be? 1 take away 0 cubed, 1 plus 0 cubed, 1 take away 3. 1 cubed is positive. 1 cubed is positive, and that guy is negative. Positive, positive, negative generates a negative result. So I now know everybody here is negative. Right, go to x equals 2 is our next one. And I'm going to get 2 take away 1 cubed, 2 plus, sorry, let's do this again. 1 take away 2. There we go. 1 take away 2 cubed. 1 add 2 cubed. Okay. And here, 2 take away 2. Let's get that right. 2 take away 3. There we go. 1 take away 2 is negative. 1 add 2 is positive, and 2 take away 3 is negative. That combination is positive. So I know everybody here is positive. Then if I look at the last one, at x equals 5, I get 1 take away 5 cubed, 1 add 5 cubed, and 5 take away 3. And in this world, negative 4 cubed is negative, 1 plus 5, that's positive. This one is positive. That entire combination is now negative. Now, in this inequality, we are trying to find the values of x that give you greater than 0, right? Positive things. And positive things are here, and positive things are here. Any value of x less than negative 1, but you cannot use negative 1. And any value of x from 1 to 3, and this is your solution. And that question is now finished. So we have essentially gone through the process for solving polynomial inequalities. What we're now going to do is to solve rational inequalities. So what does a rational inequality look like? Well, you probably could guess what it's going to look like. It's going to be a fraction greater than or less than 0. So just having a little problem with Windows there, that's why I'm pausing. Okay, so you could get, for instance, 2x take away 1 over x plus 7 greater than 0. That would count as a rational inequality. You could get 2 minus x, x minus 3, x plus 1, x minus 2, less than or equal, I'm going to make that plus 2, less than or equal to 0. You could also get that kind of guy. Now, the difference between these two and that one is that these two are really good to go. They're factored, or they didn't need to be factored. This one here isn't any use. This one would have the same kind of step one that you would use in polynomial inequalities. This one here would have to be changed into an x plus 3, x minus 3, and on the bottom, I think it's going to be what? X minus 5, yes, x plus 1, greater than or equal to 0. So essentially, if you have to, step one would be factor everything as much as possible. Okay. Now, the technique, choosing test points and all that good stuff are very, very similar. So it's not going to really be a different process. It's really just going to be an adaptation of a process that we already know. So I'm going to choose, I might as well choose this one. Suppose we've factored everybody, right? So we've got it into the format that we need to solve the inequality. So that would have been step one. Now, we find critical numbers. And this is where you have to do a little bit of adaptation. If it was only those two guys on the top, right, x plus 3, x minus 3, you would have two critical numbers, and they would be x is negative 3 and x equals 3. And since the answer is greater than or equal to 0, wouldn't we use solid dots for both of those guys to indicate you can use negative 3 and 3? Okay. And that's true. Nothing has changed. But the other two critical numbers we're going to deal with are values of x that make the bottom 0 as well. They essentially end up being vertical asymptotes if you drew the thing. But in this case, the two numbers, right, are x equals 5 and what x equals -1. But they are never usable. So it doesn't matter whether that says greater than 0, greater than or equal to 0, less than 0, or less than or equal to 0. Any critical numbers that you get from the bottom, right, the denominator, are always unusable. You might say, well, why are they unusable? I can't put 5 into this fraction. Because if I try to evaluate this fraction at 5, I would not get the answer 0. What I would get is some number over 0, right? Like 25 over 0 or -9 over 0. And we do not have a value for them, right? They're undefined. And if they're undefined, you're not allowed to use them, right? Because you don't know what they're equal to. So that's the little added thing that you just need to remember, right? Now, if that was greater than 0, wouldn't all 4 of them be open dots? Because greater than 0 means nobody can get used at any place. Now, if it was less than 0, all 4 of them would still be open dots. And if it was less than or equal to 0, you could use the top 2, but not the bottom 2. So there's your little nuance thing that you have to be aware of. Pretty much everything else is going to be identical. So I'm going to do my number line. And the smallest one I need is -3. So I'll go -4, -3, -2, -1, 0. And I need to get to 5. 1, 2, 3, 4, 5, 6 there. I got enough for everybody. Now at x equals -3, since I can use that value of x, solid dot. For x equals 3, since I can use it, solid dot. X equals 5, open circle. X equals -1, kind of overkill there, open circle. Which means that we have quite a lot of regions to get test points from. And if any of my regions happen to be positive, then that region will be in my solution. And if a region happens to be negative, that region will not be in my solution. So looking at our 5 regions, I'll choose my test points now. In this region, I'm going to do -4. In this region, I'm going to do -2. In this region, I'm going to do 1. In this 4th region, I'm going to do 4. And then this large region, I'm going to do 6. Now, you notice that I do this trick where you just plug the numbers in and decide if it's plus or minus. If that's not working for you, if you keep making mistakes or it's just not happening and you find it too hard to get your head around, simply what you could do is get your calculator and find out what that is equal to the usual way. Just type it in and you're going to get -7/8 and +42 and +1/2 and whatever. And once you know it's plus, you write plus down, and once you know it's negative, you write negative. And you don't care if it's a 42 or a 7/8. You just care that it's positive 42 or negative 7/8. Here we go. That's the expression we're going to do. So on the top, it's going to be -4 add 3. Next to it, it's going to be -4 take away 3. On the bottom, it's going to be -4 take away 5. And what? -4 add 1. If you are going to do this in a calculator, you have to be really, really, really careful about the brackets, because you will need a lot of brackets in this to get the calculator to do it in the correct order. So it's just a word of warning. -4 add 3 is negative. -4 take away 3 is negative. Those two on the bottom get me negative, and a negative plus 3 gets me a negative. And if you're not sure, how do these combine? How do I know it's plus or minus? It's the same basic rules when it's just things multiplied together. If you've got 4 negative things all multiplied together, the answer is positive. Right. I just count the number of negatives. If it's even, like 2 negative things, 4 negative things, God forbid, 6 negative things, the answer is positive. And if it's 3 or 1 or 5 negative things, the answer is going to be negative. Right. Next one. -2 add 3, -2 take away 3, all over -2 take away 5, -2 add 1. In this combination, that guy is plus, that guy is negative, that guy there is what, negative, and that guy there is also negative. So this combination of 3 negatives and 1 positive makes the answer negative. So I should be putting these in there. That lot's positive, that region's negative. Moving on to the next one. What are we doing with 1? 1 plus 3, 1 take away 3, 1 take away 5, 1 plus 1. What do I get out of that? I get 4, which is positive, -2, -4, +2, and that combination ends up being plus. So everybody here is positive. Move on to this one. It's 4 add 3, 4 take away 3, 4 take away 5, 4 add 1. And this time that's positive. Oops, get my colour scheme right. That guy's positive, so's the guy next to him. That guy's negative, that guy's positive. That combination gets me a negative. It's not uncommon to get a kind of alternating plus minus going on, but don't assume that that's the case. It's equally likely that it could go plus minus minus plus, right? There could be 2 negatives, one after the other, or 2 positives, or even 3, I guess, could happen as well. So you really have to do the check, or you don't know for sure that you're actually writing down what the correct sign is of each region. Right, x equals 6. Pretty sure that's going to be positive, but let's just verify it. 6 add 3, 6 take away 3, 6 take away 5, and 6 add 1. It looks like positive, positive, everybody is positive, which means that that region is positive. And now we're on solution, because once you've got that number line sorted out, and the answer, well, depends on what you're being asked to find. We're being asked to find when is it greater than or equal to 0. Well, that means when is it positive. So we're talking here, we're talking here, right? And we're talking about anything over here, right? Take each interval and be very careful about the numbers. So here, it's anybody less than negative infinity. So the solution would look something like this. Anybody less than -3, I should say. Now, can -3 be a solution? Are you allowed to use -3? And it's a solid dot, which means you are allowed to use it. Now, we have a -1, x is -1, to 3. So we have a union, we have a -1, and we have a 3. Now, do you notice that the -1 side, you're not allowed to use that value of x, but at the 3 side, you are. Now, what about the last region here? Bigger than 5, but can't use 5. So curve on the 5. So do you see how some are square and some are curved? Right? That value of x can be used. In other situations, that value of x is not allowed to be used. Well, at this point, I would be saying, have you any questions? But since I'm talking to myself right now, that's probably not. I'm not going to hear any answers to that. And I will make an assumption that it seems reasonable and you can work on what you're doing. So let's see if we can do just one more example of this, just to make things interesting. What one shall I pick? I'm trying to find a good one here. How about this one? This is a version of question 8. So we have 4x squared take away 81, and on the bottom we have x squared take away 64, and we're being asked to solve for what values of x will this rational function be less than 0, be negative. The bottom factoring is straightforward enough. It's a difference of 2 squares. This top one is also a difference of 2 squares, but it's not a very obvious one. Now, if that was just x squared minus 81, I know it's not, but if it was x squared take away 81, the answer would be x plus 9, x take away 9. But since it's 4x squared take away 81, it's 2x and 2x. So there, that's it factored. So not sure how much experience have you done. I know that you would have done it in 99 because I teach 99, that you would factor a guy like this. And it's still a difference of 2 squares. But if you don't have x squared, if you have a multiple of x squared, then the first term is going to change accordingly. Now, looking at these guys, we can now see who the test points are. If you want to make either of those two guys 0, the value of x, probably do it in your head, but this is the calculation for it. It's negative 9/2. So x equals negative 9/2. And since it's less than or equal to, it's the equal that's important, you can use it. And can you trust me that the other one is plus 9/2, and you can use it. And the bottom two, well, x equals negative 8, but you cannot use them, open circle, and x equals positive 8, you cannot use it, open circle. So we have 4 test points, plus or minus 9/2, plus or minus 8. So I'll draw my little number line. And I need to get, well, as far as negative 8, so how about negative 9? There's negative 8, negative 7, 6, 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now, negative 8 is an open circle. You can't use me. X equals 8 is an open circle. You cannot use me. Next, negative 9/2 is essentially negative 4.5. So it would be here. And that guy is x equals negative 9/2. And then if you did positive, it's essentially 4.5. So it would be about here. Just a little dot thing to remind me that that's positive 9/2. So we have one region here, second region here, our third region is here, and our last region is here. So I now pick test points. I don't think I have a problem with the first one. Negative 9 will work. Anywhere between here and here, so I could pick negative 5, 6, 7, 8. I'm going to pick negative 5. Anything in the third region, I like 0, so I'm picking 0. Anything in this fourth region, I could pick 5, I could pick 6, I could pick 7. Just to be different, I'm going to pick 6. And anything over here, I could pick 9 or 10, and I'll pick 10 because I want to. Now, for each one of these test points, we find out, does this give you a positive or a negative answer? So this first one is 2 times 9, so it's negative 18 add 9, negative 18 take away 9, all divided by negative 9 add 8, and negative 9 take away 8. Negative, negative, still negative. Everybody's negative, so the answer is positive. Now, if you do x equals negative 5 now, what are you going to get? Well, 2 lots of negative 5, so negative 10 add 9, negative 10 take away 9, and then on the bottom, negative 5 add 8, and negative 5 take away 8. That guy is still negative 1. This guy's definitely negative. This one is positive 3. And this one is definitely negative. And it looks like this combination generates a negative answer. Now, I could make the prediction that all of these are plus, all of these are negative, and all of these are plus. And I'd be 50-50 chance that I get it right. But I know what my luck's like. If I did that, it wouldn't work. Of course, if I don't do it, it probably will work. And I'll think to myself, well, I did a lot of work for nothing, but it's just safer. So I'm going to do the working. So 2 times nothing is what? Nothing add 9, nothing take away 9, nothing add 8, and nothing take away 8. That's a positive answer, that's a negative answer, that's a positive answer, that's a negative answer, and guess what? Yep, it was a plus. So I could make a guess that the next one's negative. Maybe it is. But I don't want to guess because I probably would be wrong. So when you plug in 6 here, you get 12 add 9, 12 take away 9, 6 add 8, and 6 take away 8. That's positive, so is that one, so is that one. There we go. Whole thing is negative. You know, I keep thinking, I'm going to risk it, I'm going to risk it. But I've always, not always, I get caught out too many times. A good prediction is that's probably plus, but it doesn't mean it will be. So let's check it. 20 add 9, 20 take away 9, 10 add 8, 10 take away 8. Yeah, everybody's positive. It was positive. And that's fine. The fact I had to do a bit more work just to be sure, it's worth it. Now, in this question, we are looking for less than or equal to 0. Less than or equal to 0 is when is the answer's negative. It's negative in this range, right? Any value of x in this range. It's also negative in this range here. So time to write down the solution. We want numbers starting at negative 8, but you cannot use it, and finishing at negative 9 halves, but you are allowed to use it, right? Negative 8 you can't, negative 9 halves you can. Union. Over here, positive 9 halves is allowed, finish at 8, but you're not allowed to use 8. And there is your solution. So what we're left with, well, there are a couple of questions that I guess you'd put into puzzles or applications perhaps. But I'd probably call these ones puzzles. And they're right at the end. And there are, I think there's 2 of them, 3 of them. There are 3 of them. Okay. So let's just show you what those questions look like. And I'll probably do one just to show you how you would approach it. I'm not sure. I'll have to do that again. It's sometimes difficult for me to see what you are saying. Right, I'm assuming that you're looking at question 9. Well, that's not the one we need. Question 10. Find all values of x for which the graph of f lies above the graph of g. So here is f, and here is g. And you're being asked, when is f above, which means when is f bigger than g? So if you were going to do that one, it would look, or at least it would start off like something like this. You're trying to solve when is f of x greater than g of x. And the f of x would be replaced by x squared, and the g of x would be replaced by 7x add 18. So there's your inequality. Now you already know that that is not the way an inequality needs to be. It needs to be factored, and it needs to be greater than or less than 0. So first thing I'm going to do is subtract 7x from both sides and subtract 18 from both sides. And now I have a nicer looking inequality, which is that one. But it has to be factored. And if you factor this one, you get x minus 9 brackets x plus 2, and it has to be greater than 0. And I've got too many graters in here. And I seem to have picked up. There we go. So can you see that the original question and what you end up solving, you have to adapt, right? You have to take that information and say, oh, if f is bigger than g, that means x squared has to be bigger than 7x plus 18. And then you do what you need to do after that. Now, question 11 is essentially the same question. When is f bigger than g? The problem is that both guys are fractions. And that's going to be quite difficult to do now. That's the version I'm going to do. And then question 12 is essentially a different version, but similar version to 12, right? It's close enough that if I do 11, I should be able to, adapt what I'm doing for question 11 and use it to solve question 12. So let's return back to our screen. So last answer, don't need that anymore. So in question 11, you are trying to solve when is f of x, which is that fraction, right, greater than, what do they call it, above g of x, which is also a relatively simple fraction. Well, what you're trying to do is you're trying to solve when is this guy greater than that guy. Now, since they only use the word above, the assumption I'm making is that you're not allowed to equal that answer, right? So that's why I'm doing greater than. This guy is 1 over x, and this guy is 1 over x minus 2. Are we good? Now, it's not really written in any format that is useful. So what I'm going to do is I'm going to do 1 over x, take away 1 over x minus 2, greater than 0. Are we comfortable with that? Now, it doesn't look very much like a rational function, a single fraction at least. We have to figure out how we're going to do that guy. If you combine these two fractions, I would multiply this fraction with x minus 2, and I'd multiply this fraction by x. And the reason I want to do that is if you want to add or subtract two fractions, they need to share a common denominator. So I look at this guy and say, he needs an x minus 2. And I look at this guy and I say, he needs an x. So I have 1 times x, 1 times 2, take away 1 times x, all over x, x minus 2, greater than 0. And that ends up being negative 2 over x, x minus 2. That is the inequality that we should be using. Now, looking at that inequality, the test points are pretty straightforward. They are x equals 0 and x equals 2. So my number line is going to have, oh, I don't know, negative 2, negative 1, 0, 1, 2, 3, 4, right? Now, since it is a fraction and the guy on the bottom, right, are both on the bottom, these two are open circles. You cannot use either of those two values. So can't use 0 and I cannot use 2, right? So they're going to be curved brackets when 0 and 2 are mentioned in a solution. So test points are going to be, well, by the way, I called that the wrong name. These are called critical points. Right, these are called critical points. The test points, well, there's my little invisible line. The test points come from each of these three regions. So I'm picking x equals negative 1. I'm going to pick on the second one, x equals 1. And in the last one, I'm going to choose x equals 3. And the guy we're going to be dealing with is this fraction here. So we have a negative 2 on the top. And we have a negative 1. And a negative 1 take away 2. So what does that look like? It looks like a negative, because negative 2 is always negative, negative 1 and negative 3. So that entire combination is a negative combination. Are we good? Hope so. Now, x equals 1 then. Negative 2 over 1 times 1 take away 2. Negative 2 is still negative. 1 is positive and 1 take away 2 is negative. So that combination gets me a positive. And then lastly, at x equals 3, I have negative 2. And on the bottom, I have 3 times 3 take away 2. What do we get out of that? Negative 2 on the top, positive 3, positive that guy. The overall effect is negative. There we go. Now we are trying to solve when is it positive? When is it greater than 0? In this case, only between here and here. So our solution is values of x from 0 to 2. And curved brackets, because you cannot use 0 and you cannot use 2. So hopefully I've given you enough help and you should be able to finish your last section that you need for this week, which is solving polynomial and rational inequalities. Okay, guys, look forward to seeing you on Thursday. Bye for now.